Well, guys, so the main topic is astrobiology, right? So you're gonna ask, hey, why do we look at Earth? Why do we look at Earth when we do astrobiology? Well, it's pretty simply. Earth is the only fucking system we have that we can actually do some science on. I mean, the other planets are not that accessible for us to look at their climate detail and stuff like this. But since the main topic is astrobiology, I think I'm gonna make a little recap from the last stream. Just a little bit. So, we know like we can put it in a easier, we can put it in connection later on with the whole Earth system model, I'd say. Mars, easy clap. Yeah. Right. We managed to get some little robots on Mars. That's not gonna help us at all. It's not helping us at all. Maybe in the future we will get way more information from that. But at the moment we don't get it. These little robots don't do much. They don't do much, right? The Mars robots moved today for 5 meters. The Mars robot moved for 5 fucking meters, guys. Can you imagine it? All right. So last stream we had the habitable zones, which was pretty dope. Excuse me, Sabitsu, I moved quite a bit. When I woke up in the morning, I had to go all the way from my bed to my PC. That's quite a bit moving I had to do there, Sabitsu. All right, so. What did we learn last time? We're just gonna recap a little bit. So, first thing we learned about the habitable zones, of course, right? That there is something called a continuously habitable zone. I have to improve my writing a lot. Continuous. Is this correct? I think I made a mistake. Yeah. Continually. Fuck. I think this is correct. Fuck. I can't write. The continuously habitable zone, which basically means that the planet should be like in the habitable zone over the whole of the star's lifetime. Like the luminosity of the star changes, of course, so planet needs to be in the habitable zone of the whole lifetime of the star, right? So planet in habitable zone of all of star's lifetime. So we did this continuously. Wait, there's an E. Continuously, thank you. You can't wait to see the first TED Talk. Hello and welcome to my fucking talk. Oh no. Alright, Ron, I probably have to tone it down a bit for my science stream, right? Should I? Okay, the constraints of during our that the Earth has itself. So the headset is constrained by planet condition, as for example, no way, science is all cursing. That's actually true. That's very much true. It's very much true, yeah. Need to put a button. See, I don't think you should shield children from that. I really don't think you should. So we had the bioproductivity as one constraint. Bioproductivity. And we will come back to this today. This is the sign for it. I just give it to you now so you can remember it later, right? We talked about the runaway greenhouse and ice house effect. Basically, at which point the planet tips, is at the tipping point that it's getting too hot and too cold and it cannot go back, basically. That is wrong. Ice house. We have the latitude of the planet, right? How the planet is tilted. And we also have the magnetic field. The magnetic field is important to keep the atmosphere, right? For example, Mars and Venus don't have a magnetic field, so the solar winds do blow the atmosphere away. Which is not good to keep an atmosphere, apparently. It depends also on the star, right? That is a no-brainer. And we had something like the UV habitable set, right? So basically, it must be in a range of radiation that is good. There's like a maximum and a minimum kind of radiation life needs to exist. And well, I mean, the lifetime of the star basically goes into continuously, has said. But it also is a constraint that if the star doesn't live long enough, life cannot really develop, right? So it's not good for the habitable zone. And we had a dynamical habitable zone. Dynamically. And what this basically means, planet needs to be in a stable orbit, right? Yeah, that's why making like a biosphere to Mars, Maximus, definitely hinges on the fact that we need to give it a magnetic field or keep it otherwise. So there is of course the question how is the rate of the how fast the solar winds blow the particles away, right? In a stable orbit. So maybe if it's not very fast, then maybe it can work if we contribute in a way that we add more and more atmosphere over time. And then we learned that there's something like the Galactical habitable zone, yeah, the galactic, which basically just says lots of areas in the galaxy are not actually habitable. In a galaxy are not habitable. Yeah, so there was this problem. Bring a magnet. Yeah, bring a magnet. Problem solved. Just bring a magnet. And then we also learned basically, yeah, you need a certain amount of UV. Like for the bioproductivity, yeah. So you needed like min, max. Like there's a minimum and a maximum you can have. Like a maximum will kill the life, and the minimum, like if it's below the minimum, it's not enough, right? And if it's over the maximum, then it will just kill all the life. And we also learned that basically you don't need to be in the classical definition of the habitable zone. And to this we come as a first point, or the second point for today, yeah? A habitable, and I say body because it's also for moons, right? Does not need to be in the classical habitable zone. Alright, so this is basically all the points we did last time to the habitable zone. And we will come back to a lot of these, for example, to the runaway, greenhouse and icehouse effects, to the bioproductivity, but also like to the last point that you basically don't need to be in the habitable zone, but also everything relates basically on the other climate constraints of a planet. Well, life needs a specific radiation maximum. Life needs it. They need a certain amount to function for photosynthetic to happen, like life as we know it, of course. When we talk about life, we talk about life as we know it. That's just how it is. So now we go to the Earth model. We could build a giant ring around Mars in orbit and power it with TEGs to generate a field. I believe Mars has the necessary materials, most likely. As for the UV, oh, we just import it. We import the UV. So, we look at Earth because we can look at it. That's basically the reason. So, we're gonna make a very basic formula of what we need for the simple model. And we have some words we don't know actually what they mean, but we will come to it. We will basically define every word, what it means that comes here. So the components we have available to us are the soil and the rocks, right? Soil and rocks. So basically Earth. We have the hydrosphere. I hope I write that correct. Hydrosphere. And the biosphere. And we have the atmosphere. How could I forget this? Atmosphere. So these are the basically 4 components we're gonna work with. Hey, Dr. Wigglesbank. We could even build that rind as an electromagnetic ring and melt Mars iron core and spin it to generate it. We can do so much. I'm sure Elon will have thought of something already, right? I mean, Elon must have a plan. He must have. So this is what we have available. So now we start. So what happens if we increase what does the sun give us? The sun gives us basically the temperature, right? The mean global temperature. This is the first point we get. You have zero faith in Elon? Why? He already bought a red car to space, yeah. Well, that car is stupid. That car will one day start an intergalactic war. I just know it. His plan is not big enough in my opinion, but he keeps changing it, so I'm not really sure. He does keep changing it? What is his actual plan at the moment? Okay, so the bioproductivity depends on this temperature, right? So we do the bioproductivity, biological. So everyone knows what's meant. Biological productivity. And basically this depends on the mean global temperature. That's what I'm not sure about his plan at the moment. I don't know. I never actually read about his plan. All I know about Elon Musk is from memes. That's all I know about him. We have the carbon dioxide in the atmosphere. Hey Ness. You click, you hear intergalactic war, what happened? You're talking about Elon's red car and how it will start an intergalactic war. So we have the atmospheric carbon dioxide. Just write CO2. And this of course, as we all know, everyone knows that by now, influences the fucking mean global temperature of the planet. Yeah, that's our problem today. So that's the problem. And now we are coming to words we don't know that much about. We have to learn about. So one thing is silicate rock weathering. Silicate rock weathering. That's how you write it, right? Yes. Also depends on the global temperature and has an effect on the atmospheric CO2, basically. It goes both ways. Then we have continental area, so it depends how much continental mass a planet has. Continental area. This influences the silicate weathering, which we learn about. And then there's a new word also, the spreading rate. Spreading rate. Basically also influenced by the continental area, at the same time has an effect on the silicate rock weathering, right? So this is like the main things we have. Well, first you wanted to nuke Mars, then you wanted to deploy fusion bombs in orbit instead, and last I heard was solar mirrors to light the dark side and poles, which was actually part of my plan combined with the ring. Ah! He wanted to nuke Mars to give Mars a magnetic field? Or the atmosphere? I'm not so sure. So, we have mean global temperature, bioproductivity, atmospheric CO2, silicate rock weathering, continental area, and the spreading rate. Main things we have. So these 6 points are getting combined in the model, basically. If you increase the solar temperature, sorry guys, it will have an effect on the silicate rock weathering. It will have an effect on the bioproductivity, and everything has to basically balance it out. So when we talk about simple model, that means there's also a dynamical model, and there's a little bit of difference. Like a simple model, you have simple kind of functions for this, yeah, it describes, both describe it over a long time scale, yeah, evolution over a long time scale. We're talking billion of years. But the simple model starts from today and goes backwards. To melt the ice caps. Oh, hey Ninja. Well, this is my third science stream. We learn physics, but she has to mention flat Earth once. No. Okay, so what the simple model does, it goes backwards in time. So that is not very good to verify. So we start today, and then we go beginning. I don't know. Back then. Back then. Yeah, that's how it goes. So it's wait, I'm not a duck. it's very hard to verify. We don't know how the weather back then was. We don't know how the climate back then was. We don't know anything back then. We can only make assumption. So that the dynamical model will go basically from the beginning to today. So that is very easy to verify. But because the simple model just goes backwards, it's not so good for verification of anything. Yeah. And it also does basically only consider the atmosphere with things and sources, a little bit of the biosphere, but it does completely ignore all the reservoirs, yeah? So only considers atmosphere with things and sources. And when we talk about things and sources, we mean CO2. We mean things and sources for CO2 basically. So partially also the biosphere, but only partially. Yeah, so we're gonna go first with this problem which we said here from the last time in the recapitulation, that a habitable body does not necessarily need to be in a classical habitable zone. This, for example, was a fact for Earth. And there is something called the faint Jørgensen paradox. I bet the nerds here already know what that is. And this basically says that we know of evidence of water, liquid water, at a time where the sun was not hot enough to actually give Earth liquid water. Paradox. So there was a time when Earth was not in the classical definition of the habitable zone, yeah? The sun was simply not hot enough. But still, we find evidence of liquid water, yeah? You want the music louder? I don't know, I would have to... Oh no, it's too loud for you. The music is too loud, you say. Okay. Is that better? You're not a nerd, you did not know about it? Tell me if the music is better. Okay, so if you go by the basic definition, we know that like the sun shines to the Earth, right? Gives the luminosity to here. And there we have Earth. So and we know like what the luminosity that goes in, that has also to come out, yeah. So L in needs to be L out. But we also know that basically a planet body has like an albedo value, so it reflects. Good morning, Andre. So a albedo value of 1 is 100% reflection. And if you have 0, it's basically 0% reflection. Okay, so the planet radiates away with black body radiation. Luminosity. And then there needs to be some kind of energy balance. And this, but that's what we talked about, the effective temperature, basically. That's effective temperature. So, by this definition, Earth would have been not warm enough to have any kind of liquid water, but it had anyway. And this is, of course, because the temperature today, this is the effective temperature. This is the equilibrium temperature. Oh, equilibrium. Basically that we need if it's in is the same as out, right? But we also have like this little bit of delta temperature, right? That's getting added by the natural greenhouse effect. And if we go by to today, like we have an effective temperature of like 15 degrees Celsius. If we had like only the equilibrium temperature, we would have been by minus 15 or minus 18, I think. Yeah, minus 18 degrees Celsius. So it would be way too cold. It would be way too cold. But because we have the greenhouse effect, which adds also something, we can live. So this is good, right? This is basically pretty good. If we wouldn't have this, I guess we would not count in the classical habitable zone, right? Can we break the graph here? I think we can. Let's see. Blue. Let's make it this. We're gonna make a nice graph. We like change the color to something maybe the same here. Yeah. Alright. I'm a red shirt? Yeah, I'm a red shirt. I don't have a blue shirt. I don't have a blue shirt, yeah. I need a science blue. I need science blue. I will get science blue one day. Not today though. She's a modern day red shirt. They live most of the time. Do they? Do they? Oh, okay. So if we go by the freezing point of water, oh, let's go this. So we make the freezing point of water, I don't know, we make it here. And we go blue. There you go. We say this is the freezing point of water, yeah? That means 275 or so Kelvin. Freezing point yeah, 273 Kelvin or something like this, yeah. And now we take the luminosity of the sun. Check the shirt color. Yeah, also I don't know. I mean, it's zero Celsius, right? It's 0 degrees Celsius. Can true on the other side, so it's both. It's whatever you need. So now, wait. We're gonna have to do the other. So this is the billion years ago. Yeah, this is the time. Yeah. So this is today. And this is 4.5 billion years ago. All right. Now we take the solar luminosity, which will be like, okay, this is gonna be a little complicated. We're gonna make another line here. That's too long. Make it. They need a triangle. I like what they have, but I need a triangle. Let's make it this. Okay, then that's not good. We're gonna remove the temperature, the 0 degrees Celsius from here, because it's otherwise confusing. So this is the solar luminosity by today's standard, yeah? You know, it's 5.5 billion years ago, man. I remember those times. Solar luminosity relative to today, yeah? So that means it's L divided by L0, and L0 is today. So there's the one, or it's 1 or 100%. Okay, wait, I need more. So yeah, so that's what it is, and there is 100%, or also 1. It's the same. And then we had something like this. Let me see if I can do it. I try my best. So it goes something like this. Yeah. So now it's today. Today. And then we know that this is below freezing point of water. Yeah. All of this is below the freezing point of water. But we had like life already here. Signs of life and liquid water. So this is not possible if Earth wouldn't have some kind of atmosphere, right? But still, what kind of atmosphere do you actually need to compensate for the way too low luminosity to go above the freezing point of water, right? So this is still kind of something that is discussed, yeah, that's kind of still a mystery. I mean, we know there must have been an atmosphere, we know that, and there must have been something. So if we had the no atmosphere, if there would have been no atmosphere, this is like the graph we would have for no atmosphere. And we would be by 80%. This would be like 80%. If Earth has always the atmosphere from today, pressure, what do you mean pressure? Oh, you mean yeah, we have to consider a lot of facts, but it's still not really I even found a paper that recently, let me see, discussed this very topic. So like it's still like something people discuss about, yeah. You can look at this, but it's probably solved more likely, more or less, right? And if we would have if Earth would have the atmosphere from today all the time, we would have something like this. Something like this, yeah? And, well, there's somewhere 90 here. So this is if Earth would have today's atmosphere throughout the whole fucking lifetime. We bring farting cows to Mars, so we are good, yeah. Yeah, exactly. We don't know exactly how this came to be. There are theories out there, like for example, one theory is that there are like some asteroids hitting Earth and adding up to this. So there are some theories how exactly this came to be. Yeah, tidal could be some, yeah. What if the rate of change? Is it like 10% per billion years, something like this, or was it? Yeah, it's not a lot. Over 1 billion year, I think we have a 10% increase. Now the temperature of Earth has been always in this region, yeah, above here. Fluctuated basically So this is the fluctuation in this range, around this minus, around this 15 Celsius. Yeah, it fluctuated, but it has always been constant in this area. So yeah, we have evidence of liquid water when the sun was not hot enough. Oh, that's bad. Was not hot enough. Yeah, tidal forces could basically plate tectonics, like any kind of plate tectonics, like any kind of volcanism, right? That would have added to that. If we would have a snowball, snow, like if we would have a snowball Earth because it was so cold and the Earth was, only covered in snow, we would have needed the snow to get dirty somehow. That could have happened by outside effects, right? Otherwise, this wouldn't have melted. Yeah, but generally, we would have needed a way higher temperature. So, yeah, that is the faint young sun paradox, basically. And you can still find people. You can make snow dirty, yeah. I don't think that kind of dirty. Exactly trying to find out the conditions we needed for this to happen. But as you can see, clearly the sun was outside of the habitable zone and Earth was outside of the habitable zone, and still it was probably habitable, right? Atmosphere is the toughest problem on Mars, but we could continuously mine the asteroid belt for water to make hydrogen and oxygen. Combined with CO2 processing and genetically engineering simple life forms, we could have atmosphere on Mars in the next minute years, if we devoted continuous effort and manpower. Yeah, I don't think this will happen. I don't think mankind is possible to be this devoted. And Vulcan, yellow snow is not enough. Yellow snow is not enough. But with magnetic induction field, we could heat Mars before we got it in the atmosphere. Yeah, it probably not happen in my lifetime. So yeah, did I miss something in this graph? I don't think so. I don't think so, guys. Could probably add that this is. On the bottom we have 225 Kelvin, just to give you an idea, right? We are not devoted to save ourselves. Yeah, we're not even devoted to save ourselves. Absolutely. Yeah, that is this point. About Mars, I feel they gonna find that the planet was clearly closer to the sun, but years make the planet go on external orbit. That's why atmosphere get fucked out. What? What? Mars was closest to the sun, and then it got driven out. Who knows? Could be. Who knows? All right, guys. So this is this. The next point, we're gonna explain the words here, right? So we're gonna start with the weathering. Yeah, we're talking about silicate rock weathering here. So this is the next point. We're gonna try to explain a bit. The equilibrium, well, and the albedo value. It takes account what comes in from the sun, but also what gets reflected. Yeah, so that's kind of the equilibrium temperature. But yeah, basically otherwise, yes. Mars isn't very big, so it lost its magnetosphere. Yeah, exactly. It also lost any kind of plate tectonics pretty soon, right? So we're gonna talk about weathering next. Gonna make a line here. Weathering is the main process that like balances out the CO2. We will see how weathering. Okay. You can read that, I'm sure of it. Hey Gabe, yes, this is a learning stream, Gabe. This is my science stream. Welcome. You missed half the class already. Not good, not good. Okay, so what basically happens, how this happens is, so we have a cloud, right? I'll make it here. We have a cloud. In this cloud there's CO2. And then it starts to rain. Headshot experiment, yeah. Oh. Yeah, I know, Savitsu, I know. Yeah, go in your corner. Yeah, go to Nash with the bad kids. Nash is where the bad kids are. We could also just send Arnold Schwarzenegger to Mars and he can terraform it in one day. Yeah. Okay, so then we have rain droplets and they merge to super rain droplets. Do we have a bad green? Yeah, there, we have a bad green. They're gonna merge to some acid droplets of water, yeah? Merge to acid droplets of water. So super not good, guys, yeah? So basically what's happened is CO2 plus water becomes this. So I don't know anything about chemistry. Yeah, when it comes to chemistry, don't ask me things. So I took that from the book and I take it for granted. Yeah. Now you remember how much you miss the planet heat maps? But they're kind of useless. So what can I do? So then we have. So what happens then here? We have land. We have a little bit of land. Yeah. And the rain falls down on the land. The acid rain, of course. Should we make it there? It's an acid droplet now. Little bit of acid. And it falls here, and then here we have a reaction. Yeah, and this is where the weathering process takes place. This is where weathering happens. There, weathering. So where do the chemtrails come into play? Well, I mean, somewhere here, Gabe, somewhere here. The rain in Spain falls mainly on the plain. What do you mean on the plain? And then we have an ocean. There's the ocean. Yeah, that's also important. I thought I'd add the nugget of wisdom. Thank you very much. Thank you very much. Acid rain would destroy much of the usable resources on Mars, but at the same time give us great insight into the development of highly acidic planets. Yeah, this is only light acid. It's not like, you know, we can go outside when it rains. We don't die from the rain, so it's only light acid. Okay, so what it is basically, weathering is a chemical reaction between CO2 and and the planet's surface. And the planet's surface. Acid rain isn't deadly. Well, not this one. It's only lightly acid. That's what. Not this one. It's only like a little bit, yeah. It dissolves in the water droplets and then it falls down, and it's slightly acid. It's slightly acid. Acid thing is a thing on Earth Park. Your car for a long time at the truck park. Watch your paint job on the car get screwed. Yes, of course. Yeah, over time it has a reaction. Yeah. All right, enjoy the dinner, Maximus. So this is what reaches the surface. Yeah, this one. Acid rain light. Exactly. Acid rain light. Yeah. So it's a slow reaction that takes place over millions of years. Yeah. Slow reaction takes place over a million of years. I see another Galactic t-shirt design coming. But what it mainly is, it is a carbon sink. No, we make that big. Carbon sink. Very important, yeah. Without the sink, if it wouldn't have the sink, we would basically have Venus conditions. We would have Venus fucking conditions. We would be hell. It would be fucking hell, yeah. So, and because of it's a sink and we are not in Venus conditions, it changes the greenhouse gas basically, yeah. Changes how much CO2 is in the greenhouse gas, right? So it's basically going to be a cycle. It's going to be a cycle, and a cycle that's basically keeps our climate stable. So the atmosphere has lower amount of it, and now we see how it comes back into the system out in the sky after it's getting stored there, yeah. So the rainwater contains this this acid elements, and then it breaks the rock down into components, and these components I cannot remember. I need to look that up because I'm very bad in chemics, so you're gonna write that down. So we have like the components that dissolves this rock, yeah. The rock dissolves in these components. So 2,3O2. So this is carbon dioxide, yeah, carbon dioxide. We write that below. Oh, I have to see that I don't come to my cam. Plus the water. What's the tea of the day? Ginger. Ginger? Not ginger. Doch, ginger. Is it called ginger? I think so, yeah. Calcium carbonate. Yeah, I don't know any of that. And this basically dissolves into ions, and these ions play an important role. Calcium ion. Then we have some more other ions. You can You can, if you know chemistry and you know mistakes, you can tell me. I don't know anything. Bicarbonate. Ions. And then we have like silicon dioxide. Ginkgo. Anything related to global warming? The topic is not global warming. So that is more like we are talking about how to get a climate stable for for exoplanets, yeah, for exoplanets. But of course, if you want to learn something about global warming, the simple Earth model is very enlightening in that way too, right? So there we have the ions. There, that is like the important stuff here. And also, there we have 2 carbon dioxide molecules, yeah? These are like two molecules. Keep that in mind. Sender sounds like a natural battery. Add lighting and see what happens. Yeah, it's just a science stream. It's just a science stream, Spider-Man. So that's a special stream, basically. Yeah. So these ions, they travel in the water through we have we have rivers here, and they transport us to the water. Yeah. And now watch what happened. There's these animals in the water, you know. There are animals in the sea, and they fucking do calcification. Calcification. I hope that word is correct. Yeah. So we have marine calcification organism using these ions and to make their bones and shells, yeah, to build their shells. And skeletons. Crazy, right? Absolutely crazy. So I don't know. So we have like corals, clams. Like there, I paint a clam. Narwhal, unicorn of the sea, yeah, or corals. I don't know. I can't paint that. Sorry, I'm bad. Well, sea creatures that do calcification. There are a lot of them, right? So what I do is use these. So these are the ions. We already know this. We don't have to write this again. So I have to look it up again. Sea lightning. This is the main reaction, the most important reaction. There are other reactions. This is just one reaction, yeah. So this is calcium carbonate. Also called limestone. But this is the most important one. And then we have a CO2 released. And we also get water out of it again. Water. And what do you see here? Before, before we had like 2 CO2s went inside. And now we only have 1. So 1 gets released. 2 molecules of CO2 get in. It's needed for the weathering, right? 1 is released back, and the other 1 is stored during the calcification. And that's why CO2 gets stored. That's why calcification is a CO2 sink, which is great. We can be happy about that. Without the sea creatures, there wouldn't be the sink, right? Pearl is made out of something, right? I know it's used as protection from particles. I have no idea about this. See, I have no idea about chemical stuff or whatever. Alright. So... so we have then the limestone getting buried here in the seafloor and stored. That's probably after they die, right? After they die, they release that and then it gets locked away. So, and the sediments will accumulate then. Will accumulate with time. Bury the old layers over new layers. Yeah, basically. So we have increased weathering. We have a lower greenhouse effect. That's basically it. Yeah. Important for this is also, so the factions that go in this is the weathering rate and the spreading rate. So what's the weathering rate and the spreading rate? We will learn that now. So spreading rate we have also here as one important thing, and the weathering rate is just basically how quickly the weathering process does happen. It is okay if you go to the toilet quickly. Yes, Vulcan, it is okay if you go to the toilet. It is allowed. Okay, so now we learn about the weathering rate. Just take your phone. Of course it's a real threat. Why should it just be a conspiracy? The planet has always been warning. If it's like we don't know what happened. We don't know what's gonna happen, right? Of course it can happen that we go to the tipping point of Venus. And there's always the possibility to go to a point of no return. I don't think that will happen. But the living conditions will decrease to a point where you don't really like living here anymore. You still live. We will still live. We will survive. It just will be a shit life. It will be a fucking shit life. So yeah, no more gaming all day. Yeah, can forget that. He's going to play Pokemon in the toilet. But it's so difficult too. It's so difficult to model. It's so difficult to see what's gonna happen. So we have to go by the data we can collect and go from there. But in general, my opinion, what's so wrong about taking care of your fucking planet? Even if there wouldn't be global warming, shouldn't we take care of our fucking planet? I don't even know why we talk about this. This is such a no-brainer. We will live in domes, like as if we were a Mars game. Yeah, probably like this. Probably like this. Yeah, in domes. Only the rich people though. Only the rich people. Poor people won't. It defies Nocturne? Yes, it does. Weathering rate. constraint of the constraint of weathering process. So we have one constraint. God, it doesn't give rich people more profit. Yeah, that's probably true, yeah. Yes, I got a Star Trek badge. Until a meteor smashes your dome. Yeah, Dr. Wigglesbang knows the way. It happens to surviving Mars all the time, yeah. Yeah, okay, we have the reaction of the mineral silicate minerals with the CO2. Then we have the transport of the weathering's products. And the third constraint is like the accumulation in the ground. Don't worry, they will make the air and sell it to us. Yes, exactly. Yeah, they will make the air and sell it to us. Yeah. If I was a superhero, I would be Storm from X-Men. I don't think so. GT would not be hero. That's your first mistake. Yeah. I don't know, Ness. I don't know what these people are about. So, what's the word here? Storage of carbonate in the sediments. Yeah? Okay. And we have to combine all these, and then we get a weathering rate F mean global weathering rate. So how quickly does the basically just how quickly does the process take place, yeah? How quickly does the process take place? Hey Vincenzo, hello. GG would be a hero, but only to her friends, cause screw everyone else. Yeah, that's how humans think. You cannot blame me for that. That's a natural human way of thinking, right? I mean, that's basically how corruption happens. It always starts with doing favors for friends. So, and in this we also have the spreading rate. Now, the spreading rate is the other process, right? Spreading rate is... Can it come out again? So we have the weathering rate. We need the balance, basically. We need the balance. So we have it stored, but it also needs to come out again. And for that we need the balance. We have the weathering rate. We put this together with the continental area, I think. Continental area. And this then equals the spreading rate. Spreading rate. And the spreading rate depends on a lot of things. It depends on the mantle temperature, we make it short, temp. On the surface temperature, on the oceanic area, and the heat flow in the mantle. You know what? This is not good. This is not good. There's not enough place. There's not enough place. We're gonna make that here. So TM TS. So now we're gonna see what this is. Just have an AI continually make predictions on this model until it comes up with 1 million matching predictions, and we might have a decent number. Yeah, basically. Enjoy the cooking, Ness. Enjoy the cooking. So this is temperature. Yeah, this is of the mantle temperature. Surface temperature. Oceanic area, and this is the heat flow of the mantle. So there's also like a difference between like the oceanic spreading rate. So we have this mid-ocean ridges so we have volcanoes, right? We go like this. So there's the water. And then we're gonna have some like mid-ocean ridges that gonna degas again. And volcanoes that gonna degas again, right? And I have something come out again. So yeah, and this is basically then what the spreading rate is all about. This is speak slowly and easy for you. It's not. I try to keep it not too difficult. Yeah, I mean, of course, if you came in later, it's probably so. Maybe we go a quick sum up, right? So this is the model we go about. There we have the mean global temperature, the bioproductivity, influenced by the mean global temperature, the atmospheric CO2 that influences the mean global temperature, and there's the silicate rock weathering that we just talked about, right? And there's the spreading rate. So the spreading rate basically influences the silicate rock weathering. So we learned that the water droplets. You made me use my brain. I'm starving. Sorry. The water droplets combined with the CO2 in the atmosphere. Yeah, they go down. In the ocean, where the marine creatures use it for their shells. It gets stored there. When they die, it gets stored on the ground. And now, if it's stored on the ground, at one point it comes out again, right? And this is defined with the spreading rate, yeah? It's basically the release of CO2 in the atmosphere again. And there needs to be a balance. There needs to be a balance between this, yeah? So, that's why we here have this balancing between, like, this is sink, this is the sink, or we make it like, wait, we make it this. This is the sink of CO2, and this is a source, CO2 source. You may also always ask questions. I repeat gladly if you didn't understand something. Yeah, that's no problem at all. Did I miss something here? I don't think I missed something here. now we're gonna go to the bioproductivity. Yeah, the bioproductivity was here in the model, and it also basically stores a little bit of CO2. But yeah, if it was too fast and I shall repeat something, just let me know. It's no problem at all. Everyone is a pleb here. I'm a pleb too. What's the time? Whoa, holy shit. Bioproductivity. And this is the sign for it. However, it's like a huge P. It's a big P. They're stealing our, but we should be glad that they steal our CO2. Like, if they wouldn't do it, we had a problem. We would have to steal it ourselves. So bioproductivity is basically biomass produced by photosynthesis. Photosynthesis. Okay, probably right. Per unit time and per continental area, yeah? So per time and area. Wow, bad writing. And it depends on various parameters, yeah? It depends here on the water supply, on the radiation, on the UV radiation. Yeah, we saw that in the habitable zone. We remember that it's important to don't have too much UV and don't have and have enough UV, right? Yeah. Like your hand, my handwriting is awful. It depends on the UV radiation, or like, let's call it photosynthesis radiation, like the one you need for photosynthesis. It's awful but efficient. I hope I'm getting better with that. This time, because it's very battery. It's okay, I guess, if I tell it, and then you know anyway what I'm saying. Hey, Dex! But, yeah. Like, nutrients. And it also depends on the atmospheric CO2. Hello, Dex! You're late to class. And on the surface temperature. But for the simple model, yeah, for the simple model, we only basically take the surface temperature and the CO2 in the atmosphere. You will be silent. No, Dex, don't be silent. That is okay. For simple model that we talking about, we only care for the surface temperature and the atmospheric CO2 pressure. That is basically what this is. Or concentration, yeah. So that's what it depends on. Yeah, bioproductivity depends on the atmospheric CO2 concentration and the surface temperature for the simple model. Of course, if we make a more complicated model, we have to take care of all of this, right? So there's, of course, also CO2 in the soil, right? In the earth. So we have the atmosphere and let's go this. So there is the concentration in the soil. So that's why we call it P soil. And there is in the atmosphere P atmosphere. Alright? So this is the two important things we have to care about. And the bioproductivity has also a maximum bioproductivity. Don't have the color. Oh, it's the right color. Okay. There we go. There we go. I like that I found that out. So if we call this bioproductivity of the surface temperature, yeah, this is only for the surface temperature. It works really well, yeah. I have to say, I think it's pretty cool. So we have 0 degrees Celsius, there we have 50 degrees Celsius, and we have 25 degrees Celsius. And then this model basically assumes that the maximum productivity, wow, this is really, really, really bad. Let's make that in 1, and let's so the maximum productivity will be at 25. So it's a hyperbole. So a parabola function, I mean. So this is the maximum bioproductivity. Now for the atmospheric one, this model will assume something like this. For the CO2, of course, for the CO2. So we have a maximum basically at 1. And below a certain point, shit, what was the number? What was the number? Something like 10. So this is the minimum, yeah? The minimum concentration we need. And below this, nothing will happen. Below this, nothing will happen. And then it goes to 1, basically, regarding the concentration of the CO2 in the atmosphere. So this is these 2 factors we're gonna put into this model. Now do the imperial. I'm sorry, Orbiter. So we basically, without CO2, no photosynthesis. Yeah, so this is the bioproductivity. And am I in time? I'm kinda at time. And now we're gonna see basically what this process does, right? So we're gonna learn about the feedbacks. So this gives us basically 2 important feedback cycles. I should have not done it like this. Okay. There. So there's a negative feedback and there's the positive feedback. So let's start with the negative one, yeah? Negative feedback. And this is basically what will balance out our climate, yeah. So negative feedback means we have a negative perturbation in the temperature, yeah? Something causes the temperature to decrease, yeah? So we have a temperature decrease. Temperature decrease. And then we have a cooler climate. And that also means that we have like less bioproductivity. And less weathering. Also the weathering rate, yeah, decreased. We have a decreased weathering rate. Probably because it rains less, right? If you have a lower temperature, I don't know, it rains less, so we don't have enough sink. Less carbon sink. And that means if we don't have enough carbon sink, if we don't store enough in Earth, it stays in atmosphere. Now, while this is happening, we still have the outgassing from the volcanoes, right? They still give the CO2 back to us. So that means in the end effect, due to a negative feedback, we will have warmer climate. So we have a warming effect. This happens, of course, over a long time scale, like over a million of years. But that means it stabilizes the climate. It keeps our climate stabilized. And this is what happens to Earth basically all the time. All the time. That is how the system responds. So if we have a positive feedback, that means we have a slight change in temperature, like an increase. That means we have like a warmer climate. In a warmer climate, we have like an increased weathering rate. I forgot the bioproductivity. But it goes with warmer climate. So if it's warmer, then we have a higher bioproductivity. So we have an increased CO2 sink. And that means in the end we get a cooler climate. Yeah? Makes sense? Does it make sense? I hope it makes sense for you guys. I hope you're still for. I hope you didn't drop out already. Okay. But this basically, this all results on the things we learned, yeah. So that I'm kind of missed a step here, but we have like increased bioproductivity here too, yeah. We have increased vegetation, and we have a decrease in vegetation. Okay, the real question is, did you know orange donors drop loot? What? I don't know. Okay, so that I guess we're gonna recapitulate now. I think we learned. Oh, the continental area. Shit, I forgot about this. Well, not really. But we see here, this depends on the continental area. We know this. So if we have more continental area, we will have a higher spreading rate. I don't know. If we have more continental area, we also have less ocean, and that means we have less ocean creatures. So maybe it should balance it out exactly. It's a good question, actually. But the continental area does influence the climate model. All right. So this is it. We have the mean global temperature. It increases, and it increases the biological productivity. It increases also the silicon rock weathering as it increases. Now, the continental area increases also the spreading rate and the silicon rock weathering. And then the atmospheric CO2 gets influenced by the silicate rock weathering and increases then again the mean global surface temperature. All right, so let's make like one nice drawing here to summarize this of the simple model. have like, there's the crust. Oh wait, oh there's like the mantle and something like this, and there's like something like mid-ocean ridges. See, I never heard of that before. Actually, I don't know anything about the ocean. Oh no, we have more Earth. So and there we have a volcano here. That's a bad volcano. Let's take this volcano, yeah. And there we have like some kind of earth and trees. So there we have the bioproductivity, yeah, the vegetation, which depends on the surface temperature and the CO2 concentration. Now we have the degassing here of CO2. So this is basically the sources. We have sinks and sources. And there's the water. And there we have marine calcification happening. And there we have like calcification is happening in the ocean. Degassing here and also here, degassing. Did I call? What did I say? I didn't call. I didn't call. Look, by the way, I actually could use some nice things. Yeah, look how nice pictures I could use. I should do that more. There you go. I said your name. I didn't say. Oh, yeah, it's true. I was talking about Vulcan. Yeah, I'm sorry. So see, look, I don't even have to draw. There you go. Nice. So there's the weathering happening. It's better you use your own drawings. Yeah, I think it's better to use my own drawings. Yeah. Did I miss something? I don't think I missed something. The acid droplets. Yeah, I missed the acid droplets. Yeah. But I drew the water too much. We have to stop with the water here. And there. There's the acid rain happening. Okay, I think I got it all. Okay, guys. So this is basically, in short, what we learned today. Doesn't sound much, but I think it was actually quite complicated. And I left all the complicated formulas out because that's not really the point here, right? But this is only the simple model. And like, for example, on Venus, this process is not taking place. Venus does not have any things anymore because Venus does not have water anymore. You feel like I'm actually there? Good. So Venus is basically only getting hotter because the volcano is releasing the CO2, and there's no water that can combine with the CO2, then go down to Earth and make a sink. So that's happened to Venus. And for example, like Mars lost the volcanic activity, yeah. So that's why like Mars doesn't have anything anymore. And the rest CO2 that Mars had, because Mars doesn't have a magnetic field, as we were talking earlier, is basically blown away by the solar winds. So I'm sure I forgot something here, but this is the basic of it. Now I'm gonna talk about it in detail about the dynamical model the next time. In detail means more than this, but I wanna tell you the difference basically. So now we're gonna have a quick look at the dynamical model. Yeah, just a quick one. Whoop. Nice. Oh, I can make a circle like this. I had no idea. So we're gonna talk quick about the dynamical model. Dynamical model. So, there's one big difference about the dynamical model. And one thing is this. Yeah, now we have coupled ordinary differential equations we have to solve. We're lucky you're about to terraform Mars or change, yeah. So yeah, that's what we have. Good, congratulations, guys. Now you have something to do. Yeah, next time I do the science stream in a month, you have this equation solved. Is that okay, Chat? Is this okay? Can you do this? I think you can do. I believe in you guys. I believe in you. So what we basically have is a lot of things to do. Yes, Rockstar, Rockstar, good. It's based on a simple model, but it just adds something more, and we will look at that. So I prepared something here. I don't have to draw too crazy. Let's see if I can. Let's see if this goes. Okay, I think that might work. That might work. So, here's the atmosphere and the ocean. Maybe we take a different color so it doesn't like. Hey, why not? Let's take this. We still need to import atmosphere to Mars. Can make something from nothing. Well, of course, you can release the stored CO2 orbital length by invoking volcanic reaction. Make an artificial volcano inside Mars. Well, yeah, I gave you the homework to solve these equations. These equations doesn't matter. Don't get worried. We will not look at them again because it's just not the point. You don't learn nothing from this. So there's the atmosphere and ocean system, and this is space. Oh wait, they write it like this. So CO plus A, yeah, O plus A. So see, this is this equation here, yeah. Can't we just fart on Mars to create CO2 and bring plants or food? Well, if you bring animals, cows, yeah, let's bring lots of cows to Mars, and then we let them fart a lot. That could probably help. Yeah. We can make a real volcano, but the atmosphere would still be a sin compared to Earth. Yeah, of course, but we can increase it gradually. You prefer equation to flowcharts? Really? Habitable, you prefer them? Okay. Good for you. Good for you. Okay. Oh yeah, by the way, we have the sun here. Ooh. There's the continents. Continents. This is the sea. The seafloor is DF, and the mantle, and the biosphere, and then the last point, biosphere. Very important, guys. Bio. Yep. Carogane. What is this? Fossil fuels. Yay! Fossil fuels below the surface. Good job. So you can see that every one of this has its own equation, basically, yeah? So we have one equation for everything, every one of these things, and these things should totally amount to 0, right? So we see ocean and atmosphere influenced. So the CO2 in the atmosphere and the ocean influences the biosphere. Yeah, this is clear. We know this already. So the position of the fossil fuels happens also through the biosphere. Yeah, it goes this way, and also at the same time it decays. I don't know, is this the decay? Probably, yeah. So there's the decay missing. Maybe there's something missing, so there's a decay happening also. What else we know? We have the regassing from the seafloor, but we also have the degassing back into the atmosphere and ocean. Yeah, we have regassing into the mantle, and we have degassing back in the atmosphere. And of course, the spreading rate that influences the continents again. So it's all basically coupled. But very important is that the total amount of these things should add up to 0. Zero CO2, right? So that's basically. So while the simple model did not consider any of the things, it only considered the atmospheric CO2 basically, and here now we see we consider all the things, and that's why it's a bit more complicated of a model, but it's a very good verification. And why? Because this model goes up in time. So it starts back then. That's what we called it earlier, yeah, and goes to today, and that makes it a really, really good verification. So we do need, though, because of that, wait, there's my thingy away. Needs initial conditions, right? So needs initial conditions. So this initial condition, so what happened at time 0. So it then calculates for a given time, I know how the climate would look like if you feed it the initial conditions, and then you get basically how the climate would look like at, for example, 4.5 billion years, yeah? How would it look like back then? So maybe the sea is not big enough. So this one is a sea, the other is a bracket. Okay, bad writing as always. So that is pretty good for verification, yeah? We feed it, we make a numerical calculation, we feed it all the initial conditions, which is not so easy, because we have to basically guess them, right? And then you see, okay, does it match up with how our climate would look today? Which is pretty cool, I think. Which is actually pretty cool. But it needs a lot of computational power, while the simple model doesn't actually need that much power. Yeah, there you solve some function and then that's it. Yeah, okay. Any questions? That was today's science stream so far, guys. What did we do? We summed up the habitable zones, and we see here now that stuff comes back, right? Stuff comes back. So the bioproductivity for the habitable zone, the runaway greenhouse effect, the magnetic field, the UV, it all comes back. And that's why we learn about these Earth system models, basically. And then we also learned about the faint young star paradox, sun paradox, so that basically the sun wasn't hot enough back then to produce liquid water, but we know it had liquid water. So there must be a certain conditions for this to happen, right? So we learned about the weathering stuff, how this happens, how we lose the CO2 and get stored in the sea floor. And yeah, the negative and the positive feedback cycle. And that's it for today, guys. That's it for today. Any questions? If you're still here and can think about the problems, and I haven't lost you on the way. That is it so far. I can put my music on again, I guess. No, I don't have to. No, I don't have to. You feel so much smarter now? You're not used to that feeling? I hope you're smarter. I hope you learned something. I hope you did learn something. I did learn something. So, and that's always good. I tried to keep it simple. But yeah, I hope you got something out of it. I will try to... Thank you guys, thank you very much. It's very important to me to get feedback, because I really like doing the science streams. I really like doing it, and I want to make it good, okay? I want to make it good. I think today I was a bit less nervous, actually. I think that I felt less nervous than the last times. Anyway, guys, I want to make it soon. The next science stream will be talking about the dynamical model a bit more, but I will probably also go into the Cambrian explosions or something like this. Yeah, because only the dynamical model, it won't be enough, because we already learned a lot of things today. Most of the things will be a repetition, and then we'll just go into a little bit more detail. I didn't have any drinks before, no. That's the aim of science, to simplify. Yeah, especially for like a Twitch audience, right? Or not a Twitch audience, for any kind of general audience. I mean, any kind of general audience. Is it a no? This is just a red shirt. It's not a legend. No, it's no working. Absolutely not. Yeah, so I will try to make the next science stream within 1 month. That would be great if I could make it within 1 month. I want to make it. I really want to make it a monthly thing, at least. So. Red shirts die first. Yeah, I want to get the science blue though. I want to get something science blue, like, you know, Star Trek has science blue. All right, guys. Thank you so much for being here. I really appreciate it. It means a real lot for me that you keep coming here to my science stream. Yeah, I can only say it. It really means a lot to me. And I wish you all a great weekend now. Enjoy your weekend. Get all the knowledge out of your brain. That's how it works, right? You get the knowledge, then you forget it. At least for me, that's the case. Hey Bionukes, and bye Bionukes, because this is the end. So yeah, have a great weekend everyone, enjoy it, have a good day, evening or night, for whatever you are on this world, and I see you again on Monday, hopefully. Thank you very much, Rockstar. Thank you very much. Much appreciated. And yeah, see you next week, or for the next science stream. Bye bye everyone. Bye bye. Alright, I play an outro song. Do we play Pippin again? Yeah, we're gonna play Pippin again. Bye bye.